Example 17.1. In this example, we have a wall that has 3 meters in height, 5 meters in width, and 0.3 meters in thickness, and has a thermal conductivity of 0.9 watts per meter Kelvin. In a particular day, it's given that the temperature in the inside of the wall is 16 Celsius and the outside is 2 Celsius. What we need to do is determine the heat loss through the wall in this particular day. We're going to take this problem to be steady, one-dimensional, and has constant properties. There are two different methods to solve this problem. We're going to solve it either by using Fourier's law or by using circuits. So let's just start with Fourier's law. Since we are assuming that this is a one-dimensional, steady, and constant property case for a wall, we know that the temperature is going to be linear, and we could determine that the rate of heat loss is going to be equal to the thermal conductivity, the cross-sectional area, the difference between the temperatures, and the distance in between the temperatures, or basically the thickness of this wall. So if we substitute all these values, we have the value K dot is equal to 630 watts. Okay, and we know that the direction of this flow is in this direction because we know that the heat travels from high temperature to low temperature. So the rate of heat loss moves in this direction. The other method to solve this is by using thermal circuits. By using thermal circuits, notice that we only have the information of what happens inside of the wall. We need the resistances and we need nodes. We only have two locations of nodes. We have T1 and we have T2. We, at this moment, we disregard what happens before the T1 and we disregard what happens after T2. We only concern what happens inside of the wall. Okay? We also know that the rate of heat loss is related to the change of the temperature divided by the resistance in between the two temperatures. The resistance in this case is a conduction resistance, and we define the conduction resistance simply as the length divided by thermal conductivity times cross-sectional area. So we simply say Q dot is equal to the two temperatures, T1 minus T2, divided by the length, K and A. If we substitute these values, we must get exactly the same result, which is 630 watts. Once again, notice that the results must be exactly the same because we're evaluating the same conduction. And the value, it is positive. That means that the direction that we chose was from T1 to T2. So notice that when we write the equations, we go from T1 to T2. So it's the from to. And the fact that it's positive, it means that the direction that we chose was appropriate.